morning, students. Today we shall study about the cutting tool materials. Cutting tools are the physical objects which can be expected to be subjected to severest of the conditions in the cutting region. Hence, cutting tools should be made of proper materials so that the machining process is successful. What are the properties desired for cutting tool materials? The cutting tool should have enough mechanical strength. So, strength in bending, strength in compression, strength in shear. Next, the tool should have enough toughness so that when it is subjected to impact loads, as in case of intermittent cutting, it will not fail so easily. Still another property, hot hardness. Next, capacity to withstand thermal shocks because of sudden cooling effects. Next, machinability and formability so that they can be processed into the required shape. Next, the cutting tool should offer low coefficient of friction in the operating range of the speeds and feeds. So if you look to all these properties, we should understand that the wear resistance, hot hardness, and toughness. These are the most important properties expected than the remaining properties. Let us study about the different materials and how these materials possess the above properties in varied manner. Let us also see what are the applications of the different cutting tool materials. The simplest of the cutting tool materials are the high carbon steels. These high carbon steels are also plain carbon steels with almost no alloying additions. Uh, they have carbon content varying from 0.6 to 1.5%. The properties of this type of steel therefore depend only on the percentage of carbon. So they are nothing but plain carbon steels, of course, high carbon steels. So percentage of carbon, if it is less, we find these tools are more tough. So lower percentage within this 0.6 to 1.5%, if the carbon content is lesser, we find the tool has more of toughness. On the other hand, when the carbon content is higher, it gives better abrasion resistance and thereby wear resistance. Both these type of carbon tool steels, they can be heat treated by water hardening or oil hardening, so that when they're quenched in this oil or water, they attain the required hardness. When we talk of the applications, they can be used for manufacture of milling cutters, twist drills, farm tools for use on free cutting materials like wood, magnesium, brass, aluminum. They can also be used in the manufacture of taps, threading dies, razor blades, engraving tools, etc. They are very cheap. They lose their hardness beyond 200 degrees centigrade. So you are not expected to use this type of tool materials beyond 200 degrees centigrade. All the workshop tools which we see, some files, hammers, chisels, anvils, sheet metal cutting snips, scissors, scribers, dot punch, carpenters. So they are all nothing but the tools made of this high carbon steels. So this is the first tool material. The next tool material of importance. So the next tool material of importance is high speed steel. High speed steels are also high carbon steels, but they contain some alloying additions. So high carbon steels, we add up some alloying elements. What are the alloying elements that have been added? So chromium, vanadium, tungsten, molybdenum, cobalt. So presence of all these alloying elements they are likely to improve the hardness, toughness, and wear resistance. These steels can retain their cutting edge hardness up to they can retain their cutting edge hardness up to 600 degrees centigrade, thus permitting higher speeds than that are possible with cutting tool carbon tool steels. So we can expect these tools to be used beyond or up to 600 degrees centigrade. So the first type of these HSS tools were made by Taylor and White. So these two scientists they propose or they brought their this first type of HSS tools to the market. So the first type of tools contain 18% tungsten, 5.5% chromium, and 0.7% carbon, and very small percentages of vanadium, steel, manganese. Right. So we can find that this type of steels, so they contain large amounts of tungsten, chromium, and vanadium, sometimes molybdenum. See, this classification of HS tools is based on whether they are tungsten based or molybdenum based, right? See, the earlier tools were tungsten based. Later on, molybdenum substitutes have come into picture. Accordingly, they are called as T type and M type. So molybdenum based steels also have tungsten, but lesser percentage of tungsten. So thereby the cost is going to reduce. The 1841, which is a popular high-speed steel, which contains 18% tungsten, 4% chromium, and 1% vanadium. So high-speed steels, they can be obtained by casting process or by powder metallurgy. Powder metallurgy tools have better performance due to the dispersion of the carbides. The HSS tools, they can use it in the manufacture of milling cutters, taps, gear hobs, shaper tools, broaches, drill bits, solid and inserted blade type cutters. Surface treatment is done to remove the burrs, improve the surface finish, which will prevent the built-up edge formation. So surface finish should be as good as possible so as to reduce the friction and thereby the built-up edge formation. Further, the corrosion resistance and skin hardness shall be obtained. So surface finishing operations for these tools, generally they are grinding, honing, shard blasting, and electro polishing. And to reduce the friction, still surface lubricating treatments are also done, which some of them are oxidizing, nitriding, sulfidizing, phosphating. Right. So this is about the high-speed steels, which are definitely superior compared to the high carbon steels. The next type of um, tools, materials, they are stellites. They are cobalt based cast alloys. So we can have combinations of tungsten, chromium, cobalt, um, and no more iron or steel. So such combinations can provide high red hardness, wear resistance, and toughness. The thermal expansion of steel and this alloy is nearly same, so that these two materials can be welded or brazed. So even that is possible. Percentage of cobalt can be 55 to 40%, chromium maximum of 25 or 30%. Likewise, tungsten 12 to 25%, and small quantity of carbon, that is 1.7 to 3%. So sometimes we can replace this chromium and tungsten by molybdenum. This type of alloys possess properties intermediate, and that means in between the HSS2s and cemented carbide. However, we have to appreciate that these are the tool materials which are having better shock resistance and impact resistance compared to the carbides, which we shall study later. So they are used in cases where there is interrupted cutting. So used in cases of interrupted cutting. So these cast alloys can be used in and therefore these cast alloys are used in the manufacture of farm tools. So the castable characteristics make them very suitable. They are highly corrosion resistant due to presence of chromium, and therefore they can be used in machining of plastic. which contain corrosive curing agents, right? So this is the third type of tool material. The next tool materials are cemented carbides. So these are the tools made by the powder metallurgy process. They display very high hardness. That is a specific property. They can have hardness up to 1000 degrees centigrade, and the wear resistance is very good. However, they have the tensile strength value which is low. Uh, if you talk about the cemented carbides, so initially tungsten carbide, only tungsten carbide. That means only WC, tungsten carbide with cobalt as a bonding material was used. Later, the carbides of titanium, tantalum, niobium have also added, and therefore the applications also improved. The carbides are the tools which are used um, very widely these days. So very widespread usage. Small tips or inserts are the shapes which are going to be made, and they are in the beginning days they were bridged to a tougher, less costly shank material, but these days they are being clamped. So how they are getting attached to the remaining shank material, it is they are going to be clamped. uh, so that is how these cemented carbides are used. Cemented carbides have the advantage of being used for a very high speeds, so that even when temperature reaches 1000 degrees centigrade also, still they retain their hardness and wear resistance. So the next type of materials, ceramics. Ceramics always have potential as cutting tool materials. They are hard, they are hard, and they retain hardness even up to 1400 degrees centigrade. It's possible, and they have less reactivity, so they can be used at very high speeds. However, they have low toughness and resistance to both mechanical and thermal loads, thermal shocks. However, the developments that have been made in the technology these days have reduced these deficiencies to some extent. The traditional ceramic cutting tool material is aluminum oxide or alumina, which is white in color, and the manufacturing is by cold pressing followed by sintering. This pure alumina has low thermal expansion. Hmm? So it has low thermal conductivity, which makes them susceptible for thermal shocks. The conductivity can be improved by addition of titanium carbide, and therefore, and after addition of this titanium carbide, the composite appears black. Addition of titanium carbide permits improvement of the thermal shock resistance. Uh, sorry, we uh, we add up this titanium carbide, but sintering is a problem. The addition of this titanium carbide improves the properties, but sintering, that means manufacturing difficulties exist. Therefore, this instead of titanium carbide, titanium nitride has been used. So the titanium nitride has been used, which improves the shock resistance as well as the possibility of cold pressing and further sintering. Zirconia is another ceramic tool material suitable for tools giving more toughness than pure alumina. If we add up this zirconia to alumina, then the tool material which we get is going to give more toughness than alumina, but not as hard as alumina. So this is zirconia alumina combination, right? Next, still another ceramic material which is popular, it is silicon nitride, Si3N4. So this metal has a very low coefficient of thermal expansion, a very low coefficient of thermal expansion, thus avoiding thermal shocks. However, the problem is the silicon nitride is not sinterable to full density. The remedy is to use silicon and nitrogen to some extent. I mean, to reduce the silicon and nitrogen in the stoichiometric quantities and add up oxygen and aluminium. Huh? Uh, okay, accordingly, we have a trade name called as SIALON, SIALON. The meaning is silicon, aluminum, oxygen, nitrogen. Yttria Y2O3 is also added to help in sintering. This CLN can retain its hardness even better than aluminum. That means even beyond 1400 degrees centigrade. The applications of this cutting tool materials is particularly in machining of the cast iron, brake drums and discs. Machining of heat resisting steels, that means titanium type of steels particularly, is another added application. So as a summary, we can understand that they can retain hardness up to 1400 degrees centigrade, have high hot hardness, good abrasion resistance, less cratering, low coefficient of expansion, right? The negative point of this type of tool material is they have low transverse rupture strength and therefore they are not used for interrupted cuttings. So not used for interrupting cuttings. One very good point about this tool materials is that they have poor wettability. So poor wettability. Therefore, they can be used even on reactive materials at high speeds. So without any built-up edge formation. Likewise, they cannot be brazed, but they can be pasted to tool shanks using epoxy resins. Next, they are also acid resistant, non-magnetic and non-conductive as well as non-corrosive. So acid resistant, non-magnetic, non-conducting, non-corrosive. Right. So these are the salient features of the ceramic cutting tools. Next, we shall talk about the cutting tool materials diamond. Diamond is an allotropic form of carbon uh, which has very high modulus of elasticity. See, for steel, the velocity modulus is about 210. For diamond, the modulus of elasticity is about 1050 gigapascals. Again, it is the hardest material known. On Rockwell C scale, the hardness is 100. Because of these two properties, one, it is high elasticity, chemical inertness, and of course hardness. It is used for obtaining a very fine surface finish and accuracy. Though the cost of diamond is high when compared to HSS and other type of tool materials, the cost per piece is low. A single crystalline diamond, it has a soft and hard axis. If it is used in direction of soft axis, it wears faster compared with usage in direction of hard axis. Diamond has the highest thermal conductivity of about 2 to 3 times that of carbides, and this results in lower cutting temperatures. So it has a very high thermal conductivity. That is also another point which has to be appreciated, and therefore the cutting is cool cutting. That means cutting temperatures are very less, relatively less. Diamond is chemically inert and takes high polish. Because of this property, chips do not adhere to the surface when machining non-ferrous and non-metallic surfaces. Diamond has high hot hardness, but excessive heat causes diamond to crack under oxidation, to crack under uh, crack because of oxidation at after 800 degrees centigrade. So we should see that it should not be subject to a sort of oxidation conditions. So abundant supply of cutting fluid to be used without any interruption. Further light cut should be employed. Diamond cutting edge is simply smooth, keen and accurate. So it's also free from sawtooth irregularities which generally occur with carbide tools. Uh, it is used in precision applications. Under proper conditions, diamond can cut 1 lakh workpieces, unlike 400 workpieces with carbide tools before resharpening. So this is one point which has to be appreciated. You can cut as many as 1 lakh workpieces before we may need to go for resharpening. On contrary, if you use the carbide tools, we can cut only 400 workpieces. So diamond is extremely brittle. It chips away or fractures if not handled properly. So it should be used carefully with minimum vibrations and protected from shock loading. So to to improve the shock resistance properties, polycrystalline diamond instead of single crystal diamond is often used. The polycrystalline diamond, it is bonded to tungsten carbide substrate and the substrate is brazed to the steel shank. That is how they are going to be used. So diamonds as cutting tool materials have various applications. They can be used in grinding wheels as abrasive materials, dressing tools, drawing dies, cones, lapping compounds. So diamond is mainly used for non-ferrous materials. Cutting of non-ferrous materials like aluminum, brass, copper, bronze, and other materials such as bearing materials. So even non-metallic materials like plastics, epoxy resins, hard rubber, glass, gold, silver, platinum, they are also going to be used for uh, cutting using diamond. In light alloy pistons, all the surfaces are diamond turned and bored, especially when silicon content is high, right? So these are some applications. So diamonds can perform very well at high speeds as well as low speeds, but only care one should take is it should never be subjected to a sort of interrupted cutting or shock loading, right? Another material of importance, it is cubic boron nitride, CBN. So this metal has a Rockwell hardness of 63 HRC. This is a material which is hard only next to diamond. So compared with the diamond, it does not burn away above 800 degrees centigrade. But if there is a presence of steam or water vapor, it breaks down chemically to boric acid and ammonia. And of course, that takes place or rather beyond 900 degrees centigrade. So CBN is successfully used as grinding wheel material and HSS tools, titanium, stainless steel, and stellite. It is used in grinding of hardened steels in the form of lead screws, bores, splines, threads, ball, roller bearing parts. CBN cuts cool, so that the grinding defects such as bursts, thermal shocks are not produced. So one common application is they are used for grinding slideways of cast iron pits. Similar to polycrystalline diamond, they are also bonded to cemented carbide substrate, and the cemented carbide substrate is clamped to the steel shanks. So they, when they are used in this protected manner, they have very high resistance and hardness, and of course shock resistance and toughness. Right. Uh, so this is about the cutting tool materials, which we call them as CBN, cubic boron nitride. See, the normal cutting tools materials, they can be coated with some of the coatings so that their properties are going to improve um, to a very high value uh, than normally expected. You can look here. If a coating of titanium nitride is provided on a high-speed steel, the tool life is increased nearly 10 times, which is a very magnificent value. Metal removal rate can become even double. Before the HS tool is consumed, more number of regrinds need not be necessary. Regarding the coatings can be done by CVD process or PVD process. Normal coating materials are titanium, TiCN, titanium carbonitride, titanium aluminum carbonitride, and titanium aluminum nitride. Uh, the coatings, the provision of coatings, they are going to reduce the adhesion wear. That means they are going to avoid crater wear particularly. Presence of this coating, it will reduce the contact length at the chip tool interface also. That is also seen. And finally, surface finish is also improving considerably. When we talk about the coating process, we can have CVD process as well as PVD process. In CVD process, CVD, the full name it is chemical vapor deposition. The tools are loaded into a reactor chamber, which is evacuated and filled with a carrier gas and precise quantities of the reactive gases. Tools are then heated to a temperature of about 1065 degrees centigrade. The high temperatures cause these reactive gases to dissociate and coat on the tool surface. So reactive gases dissociate and coat on the tool surface. When we want titanium nitride coating, titanium tetrachloride TaCl4 is a reactive gas and pure nitrogen or NH3 is supplied. So HCl gas formed during the process is neutralized since it is acidic. Uh, Temperature of the HSCs is much lower than the temperature encoded in this process. So these tools after treatment are restored to proper condition by vacuum treatment. When we talk about the PVD process, uh, the tool is subjected to a sort of deposition by a technique known as sputtering. So deposition by a process such as sputtering or reactive ion plating or sometimes arc evaporation. A high voltage between the tool, in the case of sputtering process, a high voltage is applied between the tool, which is the anode, and titanium, which is the cathode. The reactive gas nitrogen is provided. So cathode supplies the coating ions, which will be liberated by the bombardment of the gas ions. So coatings of very small thickness, as much as some 2 to 2.5 microns, can be possible, right? And the process is also relatively fast, right? So provision of this titanium nitride, for example, say we find that it's a tight adhesion for the HSS, so it is having going to provide a good lubrication or very less surface, I mean roughness. Hardness also increased, so hardness can arise to 85 instead of 70 with normal HSS. So further, there is going to be very high chemical stability and corrosion resistance, right? So these are the expected advantages on account of coatings provided on HSS. Likewise, you can provide coatings on carbides also. So coated cemented carbide cutting tool materials. So when we provide cemented carbide coating, cemented carbide tools also with the coatings, we are once again going to see an improvement in the wear resistance and toughness. So this is a insert which is coated. So the coating process again, as usual, we can use CVD process or PVD process. Titanium carbide coating, alumina coating, titanium nitride coatings are normally used. So modern days MT, TI, CN, Al2O3 and titanium nitride, they are all combined. So provision of this MT, TI, CN improves the abrasion resistance, reduced flank wear. Provision of CVD, this Al2O3 by the CVD process, um, it can provide reduction in thermal conductivity, making it resistant to crater wear, act as a thermal barrier so that plastic deformation is reduced. Again, TIN provision, so it can increase the wear resistance and wear so this type of coated tools, they are going to be generally used in turning and boring of steel, general turning of stainless steels and milling grades of this different types of steels. So when we talk of the PVD process, physical vapor deposition, titanium nitride is the first coating that was told to be useful. Later, titanium carbonitrate, TiAlN, and oxides have been also applied. So such type of tools, they can be used even on, coatings can also be used on this solid end mills and drill bits. And this majority of grades for grooving, threading, milling, such applications. Okay, so this is about coating on the continuing the discussion. We shall talk about the indexable inserts. So these inserts are called as indexable inserts because we need not use a single edge of the cutting tool. See, this is the shape of the insert. So each of them is a cutting edge, and therefore one wears away, the next edge can be brought into position and used. Further, these inserts are disposable. That means once these four edges are used completely, we can throw them away. A large number of cutting single point tools, they have been using the cemented carbide or oxide inserts. Even the milling cutters these days are using this cemented carbide inserts. When we talk about the these inserts and tool holders, we have to understand that many times they are going to be provided with negative rake than positive rake angle. So this is done so that the strength of the cutting edge is improved. Sometimes this chip breaker grooves are provided, right? Uh, the ANSI has developed an identification system to recognize this inserts as well as tool holders. So about 10 or more alphanumeric characters are provided to specify the shape, angles, what is the tolerance, type, size, thickness of the insert, bit, configuration of the cutting tool, cutting point, right? And whether it is left hand and right hand and other such conditions. Let us look to them. If you look to the details, we can find multiple of details here. The first one, it is the shape of the insert. Serial number 1 stands for the shape of the insert. The second one stands for the clearance angle. Third is the tolerance. 4 is the type of the insert. We'll see what is the meaning. 5 cutting edge length. 7 6 thickness. 7 corner radius. 8 cutting edge condition. 9 direction of the uh, cutting, that is left hand, right hand or neutral, and some other additional information. We shall look to each of these details. So first one, that is the shape of the insert. You can look, these are the shapes of insert. So there may be square or there may be parallelogram with different angles, or sometimes there may be octagonal or triangular or in the shape of a diamond. So that is one specification. Another specification, clearance angle. Clearance angle 2 degrees, 3 degrees, like that. The angle may be specified. Next, tolerances. So this is the tolerance on the thickness of the insert. So we have different type of different amount of tolerance for the thickness, so that the manufacturer should be careful enough to manufacture to required thickness. So a tolerance of 0.005 on one side, both sides are 0.125 or 0.005, right? So each of them, they may be represented with A, E, E, F, G, H, and so on, right? So generally manufacturer information is going to be followed in this case. The next information, so this dimensions L, right? That means length of the edge, or say diameter of the insert, right? So that is one. Thickness of the insert. So serial number of 2, 3, T3, 4, 5, 6, so on. So each of the thickness, say T4 indicates 4.76 mm thickness. Likewise, what is going to be the corner radius? So what shall be the corner radius, so that we get the desired finish? So eighth position, it indicates the edge condition, whether it is a neutral or zero rectangle or with a rounding off or a positive rectangle. So direction of cutting, it is also the information, it's also one more information that is provided. Um, so L stands for left hand, R stands for the right hand. So left hand cutting, right hand cutting, or say simply neutral, right? So this is the information which is connected to the inserts. Likewise, we have information regarding, just a second. So this information which is related to tool holders. Okay. So once again, in this case, we have as many as some 10 to 12 digits or 12 locations, alphanumeric characters. So the tool shank shall be provided with all this information. The first one, we call it as coupling size. That means when compared to the tool holder, what is going to be the largest dimension which fixes up with the tool holder, which we call it as C3. So D5M. So this dimension is going to decide how it assembles with the tool holder. The second one, clamping system. How we clamp. So we can clamp it from the top by having a bridge clamp or a clamp with a leg. Another information, it is tool and hole clamping, tool top and hole clamping, screw clamping. So any of these type of clamping methods can be used. Of course, some information regarding the insert also should be provided, because the tool shank has to house the cutting insert, right? It handles C type of insert which has 80 degrees as the angle between the adjacent cutting edges, or 55 degrees where in the shape of a circle or a square or a diamond with 35 degrees, and so on, right? That is another information. Next, tool holder style. That means whether the insert is simply straight or offset by a particular angle so that it stays away from the cutting tool, I mean the workpiece or the chuck during cutting. So that is called as entering angle or lead angle. So tool clearance angle, left hand tool or right hand tool, shank height, shank width, shank length, total length of the shank, right? So this is all the information that has to be provided, right? So this is regarding the inserts and tool holders, right? So this will complete the discussion on cutting tool materials, or rather unit 4 as a